Hello, everyone. Okay, I guess we're live. Okay, welcome to this week's PNS on processing memory. Today we are going to continue from where we stopped from last week. We are going to continue talking about processing using memory architectures. Just as a reminder, processing using memory architectures are a special type of processing in memory architectures that uses the analog principles of the memory cells themselves to perform some sort of computation. So the last 2 weeks ago, we talked about how we can do in DRAM row operations using processing using memory architectures. We discussed row clone. And this week, we are going to talk about how we can do something a little bit more interesting. We're going to talk about book bitwise operations using a similar approach as we use for row clone. So without further ado, the majority of this lecture today, I'm going to cover a work that I led and was published in April 2021 called SIMDRAM, which is a framework that builds on top of row clone and another mechanism that I'm going to introduce today called Embed that allows you to execute book bitwise arithmetic operations using the DRAM cells themselves. So before we start, as usual, I'm going to give a brief executive summary of what we're going to discuss today. So our primary motivation for this work is that there is a lot of interest on processing using memory architectures which can efficiently perform book bitwise operations like in DRAM row copy, as I mentioned earlier. So, however, before this work, processing using memory architectures were not quite widely applicable since they only support a limited and rigid set of operations. So they lack the flexibility to support new desired operations and often require significantly change to the DRAM subarray in order to enable more complex operations like addition or multiplications. So according to our goal in this work is to design a process using DRAM framework that can implement complex in-DRAM operations at low cost while providing the flexibility to support a desired operation with minimal modifications to the DRAM architecture. So to this end, we introduced SIMDRAM, which is an end-to-end process using DRAM framework that provides the programmer interface, the instruction set architecture, and the hardware support for efficiently computing complex operations while providing the user the ability to implement arbitrary operations as required, using a massively parallel in DRAM single structure multiple data substrate. So we evaluate SIMDRAM, and we show that SIMDRAM provides significant throughput and energy efficiency benefits compared to a baseline CPU and a high-end GPU for 16 in-DRAM complex operations. And we use those complex operations to accelerate 7 real-world applications. And we saw that SIMDRAM can improve performance for those 7 real-world applications compared to a CPU or a GPU. So here's the outline for what I'm going to discuss today. I'm going to briefly introduce again processing using DRAM architectures. So the problem that you're trying to solve over here is probably is already stuck in your mind, is that there is this bandwidth limitation between compute and memory in processor-centric designs. And moving data back and forth to the narrow memory channel that connects processors and memory devices creates data movement bottlenecks. So one way of alleviating those data movement bottlenecks is by using processing memory architectures, which moves computation to where the data resides. And in particular, here we talk about processing using memory architectures, which leverage the analog operating principles of the memory chips themselves to perform computation. So since processing using memory architecture is operated directly in the memory arrays, it benefits from the large internal bandwidth and parallelism available inside the memory arrays themselves. So a common approach for processing using memory architectures is to make use of book bitwise operations. So as I'm going to introduce next, prior work shows that we can follow a similar approach as row clone to implement simple logic operations like AND, OR, and XOR operations, and at some extent implement some limit complex operations like addition or multiplications. I'm going to briefly refresh you on the DRAM background, which is going to be necessary to introduce or to understand how the process using memory architectures, process using DRAM architectures are working. So probably this is our old news for you. A DRAM model is composed of many DRAM chips. Each DRAM chip is composed of several DRAM banks. Each DRAM bank has many DRAM subarrays, which are 2D arrays of DRAM cells. So the 2D array of DRAM cells are horizontally connected via word line and vertically connected via bit lines. The bit lines are connected to an array of sense amplifiers called a row buffer. So a DRAM cell is composed of a storage capacitor, which holds the data stored in DRAM as charge, and an access transistor, which enables and disables the charge flow from the storage capacitor to the bit line. So the DRAM cell operates using three main commands: activate, a read and write, and a pre-charge command. To reach the charge level stored in the storage capacitor, memory controller issues an activate command. So prior to receiving the activate, the bit line is held under a reference voltage, usually half of VDD. First, once the DRAM cells receive the activate command, the target row is asserted, which connects all cells along the row to their respective bit lines. Second, the storage capacitor shares charge to its corresponding bit lines. And third, the sense amplifier is enabled, allowing the resulting bit line voltage shifts to be sensed and amplified by the bit line sense amplifier. Once the sense amplifier finishes its amplification, the row buffer will contain the value originally stored within the DRAM cells along the asserted word line. Also, the charge is stored in the restored in the capacitor to its full state. At the end of the activate operation, the DRAM array is ready to receive read and write operations from the memory controller. So the memory controller then issues read and write commands to columns within the activated row. To prepare the DRAM array to filter access to the DRAM rows, the memory controller issues a pre-charge command. It works as follows. First, the capacitor is disconnected from the bit line by disabling the word line. Second, the bit line voltage is restored to its quiescent state, and now the DRAM array is ready for follow-up access. Third, the sense amplifier is disabled. So as we saw in previous lectures, we can do DRAM row copy by leverage this DRAM activation process. First, we see how we can perform DRAM row copies by copying source row A, destinational row B. So the two rows share the same bit line, and as we mentioned in prior lecture, row clone enables copying source row A to destinational row B in the same subarray by issuing consecutive back-to-back activations to those DRAM rows, followed by a pre-charge command. This command sequence is called activate pre-charge. So it works as follows. First, we send the activate command to the source row A, which will copy the context of the source row A into the row buffer. When then we issue activate command to the destination row B, which connects the cells in the destination row B to the bit line. Because the sense amplifier have already sensed and amplified the source data by the time the row B is activated, the data in each cell of row B is overwritten by the data stored in the row buffer. Let's copy the data in source row A and to the destination row B. Finally, we should pre-charge comments to prepare the DRAM array for a follow-up access. So we also can follow similar principles to execute DRAM majority operation. So in three-input majority operation, output 1, at least if two of the inputs are also 1. Let's assume that you want to compute the majority function between three rows, A, B, and C. All the rows share the same bit line. So the authors of Mbed shows that simultaneously activating three DRAM rows via a DRAM command called triple row activation can be used to perform bitwise Boolean majority operations on the values contained within the DRAM cells of the three rows. So let's see how it works. First, when we activate 3 DRAM rows, the 3 cells connected to each bit line share charge simultaneously and contribute to the perturbation of the bit line. Upon sensing the perturbation, the system amplifier amplifies the bit line voltage to VDD or 0 if at least 2 of the capacitors of the 3 DRAM cells are charged or discharged, respectively. As such, a triple row activation results in a Boolean majority operation among the 3 DRAM cells on each bit line. In this example, the majority of rows A, B, and C will be equals to VDD. The result of the majority operations is then overwritten to all the 3 DRAM cells, and to the end operation, the memory controller needs to issue a pre-charge command to prepare the DRAM array for a follow-up access. Emmet uses the triple row activation command sequence to implement Boolean AND and OR operations by simply set one of the inputs, for example, C, to either 1 or 0. The AND operation is computed by setting the C row to 0, since the majority of A, B, and 0 is equals to A and B. The OR operation is computed by setting C to 1, since the majority of A, B, and 1 is equals to A or B. So in order to perform processing using DRAM, Emmet makes use of a subarray organization that incorporates additional functionality to perform logic primitives. So Emmet splits the DRAM rows into 3 groups. First, the Emmet designated 16-row address as compute rows, which can execute triple row activations. We call this group the Bitwise group. Second, Emmet pre-initialized 2 rows with all 1s and all 0s. These rows are used to control the AND and OR logic operations. We call this group the control group. Third, Emmet uses the remaining DRAM rows as regular rows, which store users' data. We call this group the data group. Emmet requires only minimum modifications to the DRAM subarray, namely a regular row decoder that can activate rows in the data group and in the control groups, and a small row decoder that can address the bitwise group. The special row decoder can simultaneously activate 3 rows using a single single address, which perform a majority operation between the 3 activated rows. Emmet imposes less than 1% area overhead on top of existing DRAM chips. So many prior works followed up by Emmet have explored DRAM designs that are capable of performing memory computation using memory. However, 3 major shortcomings prevent this proposal from becoming widely applicable. First, they support only basic operations like Boolean and OR operations and fall short on efficiently supporting more complex operations, which limits their applicability. Second, they support only a limited set of a specific set of operations, lacking the flexibility to support a new desired operation and cater for a wide variety of applications that can potentially benefit for processing using DRAM. And some few prior works propose processing using DRAM architectures that support more complex operations. However, such designs require significant change to the DRAM subarray, which makes them costly. This highlights the need for a framework that aids the general adoption of processing using DRAM by efficiently implementing complex operations while providing the flexibility to support the new desired operations. Therefore, our goal in this work is to design a process using DRAM framework that can efficiently implement complex operations, provide the user the flexibility to support a new desired operation while minimally modifying the DRAM architecture. I will now describe our proposal called SIMDRAM. So we introduced SIMDRAM, which is an end-to-end processing using DRAM framework that provides the programming interface, the instruction set architecture, and the hardware support for efficiently implement computing complex operations in DRAM, and provides the user the ability to implement arbitrary operations as required. So SIMDRAM achieves this using an in-DRAM massive parallel SIM substrate that require minimal modifications to the DRAM architecture. I will now describe the DRAM substrate that SIMDRAM uses for in-DRAM computation. So we built the SIMDRAM framework around a DRAM substrate that enable 2 key techniques. First, a vertical data layout for in-DRAM computation. So prior work shows that employing a vertical data layout for in-DRAM computation eliminates the need for extra logic in DRAM to implement bit shifting operations, which is essential for many complex operations like addition operations. So employing a vertical data layout provides SIMDRAM with 2 key benefits. First, it enables implicit bit shifting operation. And second, it allows us to see DRAM as a massive parallel in DRAM SIMD substrate, which every single DRAM column inside a DRAM subarray becomes a SIMD lane. So the second key technique used in SIMDRAM is majority-based computation. So as opposed to using basic logic operations such as AND or NOT to implement in DRAM computation, SIMDRAM uses logic complete set of majority and NOT operations to implement in DRAM computation. So doing so enables SIMDRAM to achieve higher performance, higher throughput, and lower energy consumption compared to using basic logic operations for in DRAM computation. Based on that, we implement SIMDRAM. So SIMDRAM is an end-to-end framework that provides the user the ability to implement arbitrary operations in DRAM. The framework is composed of three main steps, which I'm going to illustrate next. It takes as input a user-defined and or not representation of the desired operation. So step one builds an efficient majority not representation of a given desired operation from its and or not basic implementation. This step takes as input a desired operation and uses logic optimization to minimize the number of logic primitives and therefore the computation limits required to perform the operation. The second step allocates DRAM rows to the operand's input and output and generates the required sequence of commas to execute the desired operation. This step outputs a microprogram, which is the optimized sequence of DRAM commands that is stored in the main memory and will be later used to execute the operation in runtime. The microprogram is stored in main memory and is going to be used to execute the operation. And a new SIMDRAM instruction called BBOP is created as an interface to the microprogram and then added to the CPU ISA. The third step executes the microprogram to perform the operation. SIMDRAM is a control unit in the memory controller that transparently uses the sequence of DRAM commas to DRAM as dictated by the microprogram. Once the microprogram is complete, the result is held in DRAM. Now let's see the first step in details. So as Embed showed, it's quite trivial to convert Boolean equations to the equivalent majority equation, as each two-input AND is implemented using a three-input majority primitive, where one of the inputs is tied to logic 0, and the OR primitive is implemented using a three-input majority primitive, where one of the inputs is tied to logic 1. Currently, the first part of the transformation process in step 1 of SIMDRAM simply replace AND OR primitives with majority primitives. However, naively converting AND OR primitive with majority primitives yields the implementation of the operation that correctly replicates the functionality of the initial AND OR NOT implementation, but is likely inefficient. To address this issue, the second part of the transformation process takes as input the inefficient majority NOT-based implementation and uses a grid optimization algorithm to apply a series of transformations that consolidates multiple majority primitives into a of majority primitives with identical functionality. This step yields an optimized majority NOT-based implementation that requires fewer logic primitives to perform the same operation to the unoptimized implementation performs. For example, this picture shows the generated majority NOT base for the carry propagation logic in a full adder, which requires only one majority primitive instead of 4. Therefore, step 1 generates an optimized majority NOT implementation of the desired operation. Let's now take a look into step 2 of the SIMDRAM framework. Each SIMDRAM operation is stored as a microprogram, which is a series of microarchitecture operations, such as activations and precharts, and SIMDRAM uses to compute the in-DRAM operation. Currently, the goal of the second step is to take the optimized majority NOT-based implementation generated in step 1 and generate a microprogram that executes the desired SIMDRAM operation in DRAM. To this end, the second step of the framework performs two key steps on the optimized majority-based implementation of the operation. First, allocating DRAM rows to operands, which assign each input operand of each majority operation to DRAM rows. And second, generating the microprogram. Now, let's take a look in the first step, to the first test. The goal of task 1 is to allocate DRAM rows to the input operands of each majority primitives in the majority node-based implementation of the operation. When allocating DRAM rows to operands, SIMDRAM takes into account two extra constraints that are specifically for processing using DRAM. First, the number of compute rows, which are rows in the subarray that are designed to perform bitwise operations, is limited. Second, perform majority in DRAM has a structured behavior. In other words, the triple row activation operation overrides the original values of the three input rows with output of the majority function. Based on these two issues, we present a new allocation algorithm inspired by the linear scan ratio allocation algorithm. Our algorithm takes as input the majority node implementation of the desired operation generated in step 1, and it starts by assigning the inputs of each majority logic primitive to the available compute rows, one at a time. Since the number of compute rows are limited, the three in this example, this step of the algorithm assigns only as many inputs to the compute rows as the number of compute rows that are allocated to any operand yet. Next, perform triple row activations in the compute rows computes the majority of A, B, and carry in this example, which in fact computes the carry out value. As a result, of the destructive behavior of the triple row activation in DRAM, the carry out is stored in all of the three input rows at the end of the triple row activation. Our allocation algorithm takes advantage of this behavior and reuses these rows for the rows to operate allocation the next round of the triple row activations in case the value stored in these rows is an input of the next majority function. Next, let's take a look at the second test of step 2. Test 2 works in three parts. The first part generates an initial microprogram. This part first copies the three operands from the data rows to the DRAM rows allocated to perform in task 1 using in-DRAM row copy operations. Once all the input of the majority are copied to the allocated rows, a triple row activation operation is performed to execute the majority logic. Finally, another row copy is issued to copy the output of the majority stored in the compute rows back to the destination row. The result sequence of the DRAM comments represents the initial microprogram. In the second step, we optimize the initial microprogram by leveraging the structure of processing using DRAM substrates, including the ability to coalesce multiple row copies operations into a single one, and merging a majority operation into a majority row copy operation into a single operation. With those two optimizations, task 2 of step 2 generates an optimized microprogram that require fewer DRAM operations to execute the same operation. So once all of the potential operations are coalesced, the framework now has an optimized microprogram that computes the desired operations for 1 bit input. The final part of step 2 generalizes these input versions of the operation into n input versions by repeating the in-DRAM row copy operations in the microprogram n times. The final output of this operation is an optimized microprogram that can execute bit 0 operations over flexible precision in DRAM. The final microprogram is then stored in a reserved region of the DRAM for future use, and also a new SIMDRAM instruction called a BBOP is created and added to the CPU ISA. The SIMDRAM instructions is used later by the programmer to perform the SIMDRAM operation. Now let's look at step 3. SIMDRAM uses a control unit in the memory controller that handles the execution of a microprogram at the runtime, transparently from the programmer. To perform a SIMDRAM operation, a program uses the BBOP instruction. Upon receiving this instruction, the control unit loads the corresponding microprogram to the BBOP from the memory and perform the required SIMDRAM operation by issuing the sequence of DRAM comments storing the microprogram of the SIMDRAM operation. At the end of the microprogram execution, the output of the SIMDRAM instruction is stored in memory. Next, I'm going to briefly discuss the system integration that we perform in SIMDRAM. So we employ several techniques to efficiently integrate SIMDRAM in a system. And the first technique is regarding efficiently transpose of data layout in DRAM that enables SIMDRAM to store the data required for in-DRAM computation in a vertical data layout. With SIMDRAM operations, since SIMDRAM operates in a vertical data layout, while the operating system implements in a horizontal data layout, make it challenging to move data between SIMDRAM and the CPU. To address this issue, SIMDRAM uses a specialized hardware unit placed between the slash level cache and the memory controller, called the data transposition unit, to transform the data layout from the horizontal to the vertical and vice versa. The transposition unit tracks SIMDRAM objects and ensures that its corresponding data is in a vertical data layout is ready for SIMDRAM computation whenever the data is in DRAM, and in a horizontal data layout wherever the data is in caches and is ready for computation in the processor. I will next present our results. So we implement SIMDRAM using the Gen 5 simulator. We compare SIMDRAM against a multi-core CPU, a high-end GPU, and embedded, a state-of-the-art in-DRAM computing mechanism. We evaluate 3 different configurations of SIMDRAM. One bank configuration, where a single DRAM bank is extended to enable SIMDRAM computation. This enables us to execute operations over 64,000 SIMD lanes. We also evaluate SIMDRAM with 4 in-DRAM compute-enabled banks and 16 in-DRAM compute-enabled banks. To demonstrate the generability, we evaluate SIMDRAM using 16 complex in-DRAM operations and 7 commonly used real-world applications for various application domains. First, we compare the throughput across the 16 in-DRAM operations normalized to the 3 baselines. Here, the x-axis shows each one of the 3 baselines we evaluate, and the y-axis shows the average normalized throughput in giga operations per second. We make the following observations. First, SIMDRAM with a single DRAM bank provides 5.5 the throughput of the baseline CPU, and this value increases to 22 times the throughput of the baseline CPU using 4 DRAM banks for SIMDRAM computation, and 88 times the throughput of SIMDRAM using 16 DRAM banks for computation. Second, SIMDRAM with a single bank is not enough to outperform the throughput of the GPU. However, with 4 DRAM banks, SIMDRAM provides 1.5 times the throughut of the GPU, which scales to 5.8 times when using 16 DRAM banks. Third, compared to embedded, SIMDRAM with 1 bank provides 2 times embedded throughput, while SIMDRAM with 4 banks provides 7.9 times, and SIMDRAM with 16 banks provides 31.6 times the throughput of embedded. We conclude that SIMDRAM can largely outperform all the 3 state-of-the-art baselines for a wide range of operations. Second, we compare the energy efficiency across all 16 DRAM operations normalized to the 3 baselines. Here, the x-axis shows one of the 3 baselines we evaluated, and the y-axis shows the average normalized energy efficiency in throughput per watt. We make the following observations. First, SIMDRAM provides 275 times the energy efficiency of the baseline CPU, 31 times the energy efficiency of the high-end GPU, and 2.6 times the energy efficiency or embedded. We conclude that SIMDRAM is more energy efficiency than all 3 state-of-the-art baselines. Third, we compare the speed up across all the 7 real-world applications. First, SIMDRAM with a single DRAM bank provides 3 times the speed up compared to the CPU, which scales to 8.7 times using 4 DRAM banks and 21 times using 16 SIMDRAM capable banks. Second, SIMDRAM with a single bank with 4 banks is not enough to outperform the GPU. However, by using 16 SIMDRAM capable banks, SIMDRAM provides an average speed up of 2.1 times compared to the GPU. Third, SIMDRAM with a single bank provides 2.5 the speed up compared to embedded, which scales to 7.3 times using 4 DRAM banks and 17.5 times using all 16 SIMDRAM capable banks. We conclude that SIMDRAM can efficiently and effectively accelerate many commonly real-world applications. So we have many more results in our paper, including the reliability of SIMDRAM operations, data threads, and area overhead in comparison to in-cache computing mechanism. I invite you to check our paper for that. So let me briefly conclude. So in this paper, we introduced SIMDRAM, which is an end-to-end process using DRAM framework that provides the programmer interface the instruction set architectures and the hardware support to efficiently compute complex operations, while providing the user the ability to implement arbitrary operations as required using a massively parallel DRAM SIMD substrate. Our evaluation shows that SIMDRAM significantly outperforms state-of-the-art CPUs and GPUs and state-of-the-art process using DRAM substrates. So SIMDRAM is a promising process using DRAM framework which can ease the adoption of process using DRAM architectures while improving the performance and efficiency of such process using DRAM architectures. So this concludes my talk. I don't know if there are any questions over Zoom. Maybe not. And next week we are going to see the problems with SIMDRAM and continue building up such processing using DRAM mechanisms for more energy efficient processing using DRAM execution. And we are going to extend SIMDRAM execution model for a multiple instruction, multiple data execution model. So I hope you enjoyed this lecture. I see you next week. Thank you very much.